paper will be presented by Alessandro Saetti, and it's a compressed path databases with ordered wildcard substitution.
I will be talking on compressed path databases that should not be confused with compressed pattern databases. Compressed path database is used for path planning. What are they? A compressed path database is a data structure that encodes the first move of all pair shortest paths in a graph. Approaches based on compressed path databases achieved a state-of-the-art performance. They have been top performance in 2 editions of the grid-based path planning competition. The size of the CPD would be prohibitively large if naive encoding was used. So previous work on CPD presents approaches that significantly reduce the size of the CPD. However, CPD can still be very large, and when the input graph is large, and this can make the approach infeasible. So in this work, we also propose an approach to further reduce the size of the CPDs. Background. Shortest paths have many applications, including games, robotics, and road graphs. In this talk, we focus on games. A popular choice to treat with game maps is converting maps into graphs by grid maps. So take this map. First, the map is discretized into a 2-dimensional array. And a cell of the 2-dimensional array is either fully traversable or fully blocked. In this figure, blue cells are obstacle, and here white cells are traversable. Then a graph is built in which nodes represent traversable cells and edges represent adjacent cells. Popular choices to treat with agency is for connected and a-connected grid maps. In our experiment, we use a-connected grid maps, so this one. Searching in the graph every time a new shortest path query is posed is usually too slow, so several approaches work in 2 phases. First, the graph is pre-processed, then queries are answered exploiting the knowledge derived during the pre-processing. And our approach also works in 2 phases. First, we pre-compute and compress all pair shortest paths data, and then queries are answered exploiting the stored data. Storing the all pair shortest paths eliminates the need for searching in the graph during the second phase, and this allows to provide optimal solutions very fast. So take this map. From the map, first we derived a weight graph. As usually done in a-connected grid maps, straight edges have a weight of 1, diagonal edges have a weight of square root of 2. Then for every node in the graph, we reindex locally its outgoing edges. Here, for simplicity, the index is the direction of the edge. And then, since all pair shortest paths data can be stored by simply caching their first move, then we compute the first move matrix, that is a square matrix, such that the cell on row I and column j is an optimal first move from node I towards node j. So the size of the first move matrix can be a strong limiting factor. So we need to compress the matrix, and the run length encoding does it. Specifically, it compresses a string by representing more compactly substrings that we call runs. Each run consists of a repetition of the same symbol. So for instance, take this string, double south, double north, triple south. It has these 3 runs. Then a run is replaced with a pair that contains the start and the value of the run. The start is the index of the first element in the run. The value is the symbol contained in the run. So for instance, run length encoding represents this string as south 1, north 3, south 6. Take the first move matrix of the previous slide. It has 49 symbols. But the run length the representation obtained by the run length encoding has fewer symbols, 32, representing 16 runs. Wildcards. So wildcard is a don't care symbol. YCard can be used to greatly reduce the first move matrix compressed by run-length encoding. To use YCard, we consider a total ordering of the graph nodes that we call the YCard ordering. Then in the first move matrix, we replace the symbol on row R and column C with a YCard, when C comes before R in the YCard ordering. So in this way, the total number of YCards in the first move matrix exceeds, is more than half than the number of matrix cells. Consider this YCard ordering and take row 6. We replace the symbols on column 2 and 5 with YCards because 2 and 5 come before 6 in the YCard ordering. This is repeated for every row in the first move matrix. And then we compress the matrix by the run-length encoding. For instance, for the first part of row 6, it becomes 1 northwest. The second part becomes 7 east. And the CPD that we obtain using YCard has 5 runs fewer than without YCards, but of course the saving can be much greater for large maps. YCards remove some information from the first move matrix. However, the information remaining in the matrix is sufficient to reconstruct the optimal path. Indeed, for any pair of nodes I and j, exactly one of the cell ij, ji is preserved in the matrix. The other one is replaced with the YCard. The procedure answering queries is the following. If j comes after I in the YCard ordering, take a forward move from I towards j and continue recursively. Otherwise, take a backward move from j towards I and continue recursively again. So for instance, consider the path from 3 to 5. 5 comes before 3 in the YCard ordering, so we take a backward move from 5 to 3. This is done by a binary search on row 6, on row 5. The search finds that 3 is in this run. The value of this run is north, but since this is a backward move, it becomes south in the path. Then we continue recursively, constructing a path from 3 to 4. 4 comes after 3 in the YCard ordering, so a forward move is available, it is west. And finally we construct a path from 2 to 4. Again, 4 comes after 2 in the YCard ordering, so a forward move is available. Again, it is southwest. After this move, the two segments, the forward segment 3, 2, 4 and the backward segment 4, 5 have met, and the optimal path is complete. In the paper, we show that using YCards in a way that maximizes the memory saving is NP hard. So since finding the optimal ordering is too complex, here we discuss two suboptimal orderings. These orderings derive from two existing heuristics, CAT and DFS, that have been previously proposed by Strasser and others. In that work, these heuristics are used to order the columns of the first move matrix, while here we discuss their use to order YCards. CAT constructs the ordering recursively. It divides the graph into two subgraphs and requires that all nodes in one subgraph come in the heuristic ordering before all nodes in the other subgraph, and then it continues recursively. DFS orders the node in the order in which the nodes are visited for the first time in the first traversal of the graph. The intuition captured by these heuristics is that the nodes close to each other in the map should come close to each other in the column ordering. So using these heuristics to order column, it's more likely to have longer runs in the first move matrix. So to effectively reduce the number of runs using YCard, it's more useful replacing consecutive symbols with YCards in the first move matrix, and this can be achieved when these heuristics, CAT and DFS, are used to order both columns and YCards. We have seen that YCards can increase the time before the first optimal forward move is known. In the previous example, one backward move was needed before getting the first forward move. But using CAT and DFS to order YCards, this could be much worse. Consider a source node S and a target node T such that T is less than S in the wildcard ordering. This means that a backward move from T towards S is available. And let T prime be the new target after performing this move. Since T and T prime are neighbors in the map, it's likely that they are close to each other in the wildcard ordering. And since T is less than S and T prime are close in the wildcard ordering, it's also likely that T prime is less than S in the wildcard ordering, and so a backward move is again available from T prime towards S. Applying this argument recursively, it could happen that several backwards moves may be needed before getting the first forward move. So we have developed some heuristics to reduce the first move's lag, breaking the chain of backwards move as early as possible. One of them is cut random. Cut random starts from the cut ordering and simply swaps the ordering of k pair of nodes picked at random. The second type of heuristic that we used, that we called TK, controls the number of used wildcards. The idea is to skip the applications of some wildcards, leaving moves available in both directions, forward and backward. So we are free to prefer a forward move, breaking a possible chain of backward moves. Take a cell. Tk has two parameters, R and K. Take a cell as T that will be replaced with a wildcard according with the wildcard ordering. If for cut Tk, if in cut ordering the difference between the indexes of source node T and target node T exceed the parameter R, and T is a multiple of parameter K, then Tk does not replace the cell as T with a wildcard. Otherwise, it applies the method as before. Basically, parameters R and K control how many wildcards to skip. The larger R and K, the few wildcards are skipped. DFS random and DFS TK make the same with DFS. Experimental results. We have developed our idea on top of the state-of-the-art system SRC. Our benchmark consists of 8 connected grid maps from 185 game maps. The number of nodes in our map ranges from quite small maps with about 2,000 nodes to large maps with 750,000 nodes. And the performance is evaluated in terms of size of the CPD, number of lookups for getting 1 and 20 forward moves, and time to compute a full path. This table shows the effectiveness of using wildcard when the cut column ordering is in use. We obtained a similar result using DFS instead of cut. Wildcard ordering cut reduces the CPD size by a factor of 2 in average. It is also better than a random order that reduces the CPD size by about 28%. On the other hand, as expected, the first move's lag increases significantly for cut. And this means that using wildcard, there can be a trade-off between the CPD size and the first move's lag. Heuristics cut TK and cut random help balance this trade-off. For instance, take TK 10.5. It cuts the CPD size by about 42% and reduces the first move lags significantly from 85 to about 6, from about 100 to about 24. The aim of using wildcards is reducing the CPD size, but we have surprisingly observed that they can slightly improve the full path time. This happens because with a smaller CPD in use, the rate of CPU cache misses could be smaller, and since compressed rows are shorter, the binary searches are slightly faster. This slide shows the first move lag when cut column ordering is in use. DFS leads to a similar behavior. And here we show how TK can improve the first move lag of cut. TK reduces the first move lag from very large values, hundreds, to small and stable values, units. In summary, CPD-based path planning systems achieve an impressive speed performance in terms of time to compute the full path. However, large maps, we say that large maps can lead to large CPDs, and this can be a bottleneck of the approach. We have observed that more than half of CPD symbols can be replaced with a don't care symbol, a YCard. And we have also observed empirically that YCards can reduce the CPD size but greatly increase the first moves lag. So we have proposed and evaluated the heuristics that balance this trade-off. And using these heuristics, the CPD size reduces significantly again, and the first moves lag remains competitive. We are currently studying new heuristics and techniques for reducing the CPD size by YCards. So that's it.
So, if I'm not mistaken, this is mainly, or this is only applicable to graphs where you have undirected edges. So, if you have a from I to J, you have the same. So you have the inverse path from J to I.
Actually, yes. We are trying to extend this idea to direct graph, but we are not completely sure that it can hold for directed graphs.
And on one of your slides, I had the impression that I think you had results for a random strategy for finding this wildcard, and compared to yours.
Which slide?
One of the very last ones, I think. I think maybe this one.
Yeah, we have also compared our heuristics with the random order of YCards. So this, let me see.
It was just
this ordering has been
the random order works. So.
Yeah.
It's really important to have these heuristics, it seems.
Yeah.
Oh, yes.
So I may not have understood everything perfectly, but I'm just curious, have you looked at the idea of canonical orderings where you put a single path between the start and the goal, and then you can do variants of that. You could try and get more compression by sort of encoding your heuristic into your actions. Does that make sense?
Encoding, say it again.
Your heuristic tells you to do something, right? So you have this default knowledge of your heuristic, and you can use that as information to help your compression.
Actually, the knowledge has been pre-computed during the first phase. So we use Dijkstra for computing the optimal paths. The heuristics are used to compress the knowledge pre-computed during the pre-processing.
I'll talk to you later. I'll try and find you and ask more detailed questions.
Okay.
Okay, well, thanks, the speaker again.